Hi Pre-Calc, welcome back. Today our objective is going to be to find derivatives and to be able to define derivatives. So I've got the checklist on the screen. You know what to do from here. So quick review, do you remember how to write the equation of a line that goes through the point x1, y1 and has slope m? If not, go ahead and write this down with me. It is y minus y1 equals m times x minus x1. This is called point slope form of a line. And this is the form we use the most in calculus. We use this pretty much every day in calc. So make sure that you've got this written down if it's not one you're super comfortable with, because we're going to be using this a lot for the remainder of the next two lessons. All right, so just some review from last time. Remember that we drew this graph of f of x last time with x starting here, and then we move a distance of h over to land at x plus h. And then our y values would be f of x here and f of x plus h here. So when we do the slope, when we do rise over run, the change in y is that top y value minus the bottom y value all over your run, which would be this x value minus this, which just gives me a run of h. So that's the slope of the secant line, that green line. But then remember, in calculus, our goal is really to find the slope of the tangent line, which is the slope at one point. And the way we did this was to force this distance h to approach what? Do you remember? To approach 0. So we want this distance to become infinitesimally small. So the slope of the tangent line is this difference quotient as the limit as h approaches 0. So limit as h approaches 0 of the difference quotient, this f of x plus h minus f of x all over h, right? And this is a very, very important limit in calculus. The slope of the tangent line is formally given by this limit, and we have a very important word for that, and it is called the derivative, okay? So the derivative is denoted typically as f prime of x. Will you write that in your notes for me? And the way we define f prime is the equation that gives us the slope of the tangent line at any x value. And remember, the way we find that is that limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so this is how we find the derivative. This is the notation, so it's f with looks kind of like an apostrophe x. The way we pronounce this is f prime of x. So that's how you say that, f prime of x. Another notation you may see is dy dx. It looks like a fraction, but it's not. You don't say dy over dx. This is another notation, kind of like how we have y equals or f of x are the same. This kind of analogous scenario here where you can have f prime of x. This is typically how you'll see it in pre-calc, but just so that you know for next year, you may also see it as dy dx. Should kind of look familiar, like delta y over delta x, because it's your change in y over change in x. This happens to be as your change in x approaches 0. All right, so calculus has two branches, and one of the branches is called differential calculus, and it's all about the study of the derivative, which is slope, right? Okay, and its other branch is integral calculus, which is really a big idea, is like sort of the area underneath the function. And we're going to be looking at that branch a bit later as well. This first branch is called differential calculus because it's the study of derivatives, okay? And the derivative is what again? It gives you the slope of the tangent line, okay? So let's take a look at this line. We've got y equals 4/3 x. I've got it graphed for you here. Does the rate of change ever change? Does the slope ever change for this graph? No, it does not. The rate of change is always what? What's the slope? The slope here is always 4/3, right? So for this function, its derivative is always going to be 4/3 because no matter where I choose to zoom in, I'm always going to get 4/3. It doesn't depend on what x value I choose. any x value I choose to zoom in on, the slope will always be 4/3. So this derivative, notice there's no x after the 4/3. Your derivative is just a constant 4/3. Force pause on the screen. Can you go ahead and copy the function for part A as well as the point or the x value x equals 3? All right, we are back. So we want to find the slope of the tangent line to f, which is 10x minus 2x squared at x equals 3. And the slope of the tangent line is what word in calc again? Derivative. And how do I denote that? We denote that by f prime. So in this case, I want to find f prime of 3, right? So let's go ahead and write the formal definition, and then we'll work with that to see if we can get the slope right at x equals 3, all right? So f prime of 3, I'm going to take that limit definition, the limit as h approaches 0 of the difference quotient, but what am I going to plug in for x? I'm going to plug in 3. So we'll have f of 3 plus h minus f of 3 all over h, right? So let's do this kind of step by step. So let's find f of 3 plus h first. So coming to our function, anywhere we see an x, we're going to replace it with parentheses 3 plus h, okay? So we've got the limit as h approaches 0 still. So this part, I'm going to have 10, and then I run into an x, so I'm replacing it with 3 plus h. Minus, keep going here, you have a 2 next. Now I run into another x, so I'm replacing that with the quantity 3 plus h squared. Okay, so all of this is f of 3 plus h, right? Now I want to go minus, keep going with your formula, minus f of 3. All right, so if I plug in 3, now I get 10 times 3, so that'll be 30, minus 3 squared is 9, 9 times 2 is 18. Right, so that orange piece is f of 3, and then it will still be all over h. Okay, alrighty, so we've got limit as h approaches 0. Now let's work with the purple. Shall we distribute the 10 first? So that'll be 30 plus 10h. And then I still have the minus 2. Now be careful because you want to do exponents before you multiply, right? So let's distribute this, or let's do 3 plus h squared. So that will be 9 plus 6h plus h squared. And then I still have my minus, I'll go ahead and distribute that negative, minus 30 plus 18 all over h. Okay, so cleaning this up a little bit, I can see, well, 30 and minus 30 are going to go away, right? And look, this negative 2 times 9 is going to be negative 18, and then I've got a positive 18 here, so those will go away. So let's rewrite this. We've got limit as h approaches 0, and I still have this 10h. Then distributing this negative 2, this is going to become minus 12h. And then negative 2 times h squared will be negative 2h squared. And I still have that all over h. All right, combining like terms in the numerator. We have 10h minus 12h, so that's negative 2h minus 2h squared all over h. And now we can factor out an h in the numerator. So that gives me h times the quantity negative 2 minus 2h. Then you get this nice cancellation because h divided by h is 1. And then lastly, plug in 0 for h here. So this is going to be negative 2 minus 2 times 0, which is negative 2. All right, so just kind of a quick check on the calculator. What did we just find again? We found the slope of the tangent line at x equals 3. So I've got blue dot at x equals 3. I've got our function graphed. So if we zoom in on that blue dot until this starts to look linear, so until I lose that curvature, now I can kind of count the grid. So I go down 1, 2, to the right 1. That is indeed a slope of negative 2. So it looks like we did pretty good there. All right, part B says find the equation of the tangent line at x equals 3. So now I actually want to find the equation of the line that would be tangent to that red function we had at that blue point. So always start, when you see equation of the tangent line, always start with point slope form. And when you have point slope form, you've got to fill in numbers for y1, m, and x1. Now typically they'll tell you what x1 is. So in this case, we're looking at the value x equals 3. So that's what we're plugging in for x1. Okay, now remember this x and this y are your variables. So we're going to plug 3 in for x1. We found m in the previous part. What was the slope? The slope was -2. Remember, that's what we got when we zoomed in as well. So now all we really need to find is y1. So how are we going to find y1? Well, y1 is what is y when x is 3. So we're just going to plug 3 into the original, which, by the way, we did that over here in the orange piece, right? That was, we ended up getting 30 minus 18, which is going to be 12. So coming back to our point slope form here, we're going to get y minus 12 equals -2 times the quantity x minus 3 as our final answer. Let's confirm that equation with our calculator. All right, so here is our function. Here's our tangent line. It zoomed in enough, these two should start to look identical at that point of tangency, so this looks great. If I zoom back out, you can see that hugs the curve really nicely right at the point 312. So that we did good. First pause on your screen, can you go ahead and copy this function and the x value 1? All right, so we want to write the equation of the tangent line. Again, as soon as I see this phrase, equation of the tangent line, I'm going to think, okay, my final answer needs to be in point slope form. All right, they gave me x1, that's 1. How would I find y1? Well, y1 is going to be whatever f of 1 is, right? So that'll be 1 over 1 plus 3, so I'm getting 1/4 for y1, okay? Now, to get m, I need the what? I need the derivative, all right? So for m, that is going to be f prime of 1, all righty? So remember, the formula for the derivative is the limit as h approaches 0 of the difference quotient, so change in y over change in x. So in our case, we'll have f of 1 plus h minus f of 1 all over h. So taking that generic formula but replacing x with 1. All right, so let's go step by step here. So let's find f of 1 plus h first. So I'm going to do arrows so I can drop that limit notation at the front. So f of 1 plus h. Well, anywhere I see an x, I need to replace it with quantity 1 plus h. So I'll have 1 over 1 plus h plus 3, right? We'll do parentheses here for now. And then minus f of 1. Well, we said earlier, f of 1 was going to be 1/4, right? And then we'll have all over h. Okay, let's clean this up a little bit. That purple piece, notice that you have a 1 and a 3. Those are like terms in the denominator. So 1 plus 3 is 4. So let's change this to h plus 4 and keep everything else. Minus 1/4 all over h. Now, remember when we did these limits, do you remember algebraically what we can do now? So now what we want to do is get a common denominator, and just so that it's not too much to look at right now, I'm going to block this out just for now so we can really focus on the purple and the orange. So notice that you've got two different denominators, right? So one has is a denominator of h plus 4. The other denominator is 4, and you need both factors. So the first fraction is missing a factor of 4, so what I multiply to the denominator, I need to do to the numerator. The second fraction is missing a factor of h plus 4. Again, what I do to the bottom, I need to do to the top, okay? So now they have a common denominator of 4 times h plus 4. So I can go ahead and subtract the numerator straight across. So I'll have 4 minus h minus 4, right? Well, 4 minus 4 is 0, so really I just end up getting minus h in the numerator. You with me there? All right, let's bring this guy back. And this is going to be all over h. But now, cleaning this up, I've got negative h all over 4 times the quantity h plus 4. Then I'm dividing by h, which is h over 1. But dividing by h over 1 is the same as multiplying by its reciprocal 1 over h. H divided by h is 1. Those go away. So don't lose your placeholder of negative 1 in the numerator over 4 times the quantity h plus 4. And then my last step is going to be to apply that limit as h approaches 0. So when I do that, I get negative 1 over 4 times 0 plus 4, which gives me a 16 in the denominator. So let's try it. Our final answer then, coming back up here to the point slope form, will be y minus 1/4 equals negative 1 over 16 times the quantity x minus 1. Let's check this in Desmos. All right, so here's our function as well as our point of tangency, 1 comma 1/4. Here is the equation of the line we got, which looks great, right? If I zoom in on that point of tangency, notice that our function and our tangent line start to look identical around that point of tangency. All right, so let's close this out with scenarios where, are there scenarios where the slope of the tangent line does not exist at a point? So let's look at some examples. Remember, what is the slope of a vertical line? The slope of a vertical line is undefined, right? So here's an example of a vertical tangent line. If I zoom in enough at the origin here, you can see that that is going to be a vertical line, right, which has a slope undefined. Okay, so if you've got any vertical tangent lines, we say that the derivative does not exist there because the slope is undefined. The slope does not exist. Okay, another situation, kind of similar, is if you have what we call a cusp. Okay, so watch what happens when I zoom in here. See, once again, this starts to look vertical. Okay, so you can see that this starts to look vertical once again due to that cusp, and again, vertical lines have slope undefined. All right, so cusps like this one, or graphs that have a vertical tangent line like this one, they do not have derivatives at those points. They have derivatives elsewhere, right? But not in these two, not at the origin. Another problem is if you've got a corner, like an absolute value function, because if I keep zooming in at the origin there is no way for me to get rid of that corner. So you've got a slope of, if you can count the grids, -1 coming from the left and +1 coming from the right. But at the origin, no matter how much you zoom in, you're never going to get just one nice linear function, okay? There's no way to get rid of that corner. So anytime you have a corner or a cusp or a vertical tangent line, there is no derivative at that point, okay? Last scenario I want to show you is if you've got a discontinuity like this, okay? So if you've got a discontinuity, if I try to zoom in, I'm just going to get eventually empty space, right? So this also certainly does not look like a linear function, okay? So if once you start to zoom in and you don't get a linear function, then there is no derivative there, right? Because the derivative is the slope of that linear piece once you start to zoom in enough. All right, you all, that is what we have for today. I will see you next time.